Hello everyone, and welcome to another session on seismic analysis with IS1893. I am Surajit Ghosh, and in this session, I'll cover an important topic: how the design horizontal acceleration coefficient AH is calculated and used for static seismic analysis. This AH value depends on several factors, including site-specific condition and building-related parameter. I'll discuss all these factors used to calculate the AH value. In last video, we discussed how seismic ground acceleration is applied on any structure as an inertia force, and how design base shear is computed and distributed along height of the structure. You can check that video for more details. Design base shear VB is equivalent to an inertia force, which depends on the mass and acceleration of the body. If we consider clause 7.6.1, we can notice an identical equation: weight of the structure and a factor AH, which is termed as design horizontal acceleration coefficient. We have already covered how we can define seismic weight or mass model for static and dynamic analysis. Today, we will discuss about this AH factor, which depends on the approximate fundamental natural period, TA, and direction of earthquake. As per the inertia equation, we are expecting an acceleration term, right? If we check clause 6.4.2, we can notice this AH is a coefficient which depends on several factors like Z, I, and R, including a design acceleration coefficient SA by G, which is not the seismic ground acceleration. Do you know how this is calculated and used for seismic analysis? It is the most important factor and used both for static and dynamic analysis. As per IS 1893, SA by G is normalized with peak ground acceleration, depends on the soil class, natural period, and damping of the structure. There are few empirical equations available to calculate this for different soil condition and time period. For static seismic analysis, we need to follow the first set of equation. For dynamic analysis, second set is used. Same values are plotted under figure 2, both for static and dynamic analysis. Depending on the site-specific soil class, 3 separate curves are provided, and if we want to compute SA by G, we need the time period of the structure. By the way, these equations and curves are plotted for 5% damping, and for other damping percentage, SA by G value is modified. This modification factor is not available in IS 1893-2016, though it is mentioned under table 3 of IS 1893-2002. In summary, first the natural period of the structure is calculated, and using that, we can compute SA by G using these equations or the graph. Soil class is available in the soil testing report of the project. It is easy. But what is this coefficient and how this is related to the ground acceleration? During earthquake, ground acceleration is recorded and plotted against time in different axes, which is known as the accelerogram. This data is recorded for all types of earthquake in different zones, whether it is high seismic zone like Bhuj or low seismic area like Bangalore. This data is used later to find out the structural response of a scaled model. Either a computer program or sec table is used to simulate same earthquake acceleration on a scaled model, and structural response in terms of acceleration or displacement is recorded in a time history plot. This scaled model is known as the single degree of freedom system or SDOF. What is a SDOF system and how it is related to any real-life structure? That is a complex topic, and I am not going to discuss this today. This SDOF system has a specific stiffness and time period, and from this simulation, maximum structural response against that recorded ground shaking is recorded. Then same steps are repeated for another STOF system with different stiffness. As fundamental time period depends on the stiffness, Second system has a different time period. When a STOF system is disturbed from its position, it starts to swing back and forth like a pendulum. Time required to complete one complete cycle is known as the natural period, and it depends on the stiffness. More stiff structures displace less and have a lower time period, whereas ductile structure takes more time to complete a single cycle. If we change the stiffness, time period will change, and for same ground acceleration, structural response will be different. So, if we record the maximum acceleration of different STOF system with different time period for a single earthquake data, that will generate few data points on this graph. This response is not plotted directly. It is compared with the gravitational acceleration. So, it is no longer an acceleration, rather an acceleration coefficient SA by G, and that value is plotted in a graph over time period. This graph of maximum response versus natural period for a given accelerogram is known as the response spectrum. This data is obtained for a single earthquake. Next, same steps are repeated multiple times considering different ground acceleration data. This provides plenty of data point on the graph with higher accuracy. But if we plot this, it will be a scattered curve with several peaks and valleys. We have considered mild to severe earthquake, for which peak structural response should be different. Also, same structure might respond differently when a different earthquake is repeated in the same site. If we use this graph to calculate SA by G value of any structure, a slight change in natural period will lead to a large variation in maximum acceleration. This is not realistic, as we cannot even compute the natural period precisely. For design purpose, this curve is smoothened as much as possible without affecting the maximum response quantities. This smoothened curve is presented in IS1893 under figure 2 as response spectra curve. I think it is clear now how this graph is plotted considering different earthquake data, and using this, we can get the maximum response or acceleration coefficient of a STOF system. By the way, structural response depends on damping, and this graph is plotted for structures with 5% damping. I will discuss later how different damping values are used to calculate the base shear. Also, structural response depends on the soil condition, and any variation in ground motion for different site is considered using different shape of response spectrum. That's why separate curves are provided to handle structural response at different site. There is one problem with this approach. We have considered all recorded earthquake data to plot this curve, and if we calculate SA by G of any structure, that no longer depends on where the structure is located, whether it is in Guwahati or Kolkata. This is not logical. We need to design a building in high seismic prone area considering higher lateral force, right? To consider different intensity of shaking in different seismic zone, a factor is multiplied with this SA by G value, which is known as the zone factor Z. India is divided in 4 seismic zones depending on the seismic activity, and these zones are mentioned in this map. Also, seismic zone information of several locations is provided in Annex E, and we can cross-check the project site zone from here. It starts from Zone 2, which has minimal seismic activity, and ends with Zone 5, which has the highest seismic effects. Zone factor is available in this table, also in table 3. For each zone, peak ground acceleration is recorded, and a reasonable value is used as the zone factor. For seismic zone 5, the factor is 0.36, which means a peak ground acceleration of value 0.36 G is expected in this zone, whereas same PGA in seismic zone 2 is just 0.1 G. This is an estimated value, and there is a chance that during earthquake, peak ground acceleration might cross this limit. Using this factor, we magnify the SA/G value and seismic force in different zones. For example, PGA of zone 5 is 3.6 times more than the seismic zone 2, and all forces are accordingly multiplied with this factor. During seismic design, we assume that the structure will undergo some damage during strong earthquake, and for any important structure, we try to reduce this as much as possible. For example, any building which is used for communication, like a hospital or radio and station building, we try to design these structures as robust as possible without any significant damage. That's why there is an additional multiplication factor to increase the design force and reduce the damage for seismic activity. All structures are divided in 3 categories as mentioned under table 8, and different factors are used. 1.5 for critical structure, 1.2 for all residential and commercial building with more than 200 occupants, and 1 for any other structure. Till now, we have calculated the design acceleration coefficient SA/G based on soil condition and natural period, multiplied it with a factor to consider the peak ground acceleration in different zones, and an importance factor. This SA/G into Z into I is the maximum elastic acceleration, and it represents the MC level earthquake. MC is the maximum expected earthquake for any region. It is not defined properly in IS1893, and if we consider any international code like International Building Code 2000, it is an earthquake having a 2% probability of being exceeded in 50 years or 2500 year return period. Similar logic is mentioned in Uniform Building Code with 1000 year return period. It is a long duration, and expectancy of this level of earthquake in the entire lifespan of a building is nominal, which means we are considering an earthquake effect which is not reasonable. Section size and required strength will be huge. For more realistic design, we consider a lesser amount of force which is known as the design basis earthquake or DBE. IS1893 does not specify any probability or return period, and as an empirical approach, design basis earthquake has been assumed as half of MCE level. That's why there is a term 2 in the denominator to reduce the MCE level earthquake to DBE level. There is another factor R in the denominator to reduce the seismic force. Before I explain this, let's revisit one important design philosophy of seismic analysis. We always assume that a structure can damage during a moderate or strong earthquake, else the structure will be uneconomical. Any structure should be designed for earthquake in such a manner that for minor and frequent earthquakes, there should not be any damage. For moderate earthquake, there might be some minor damage to the non-structural element, but no major structural damage. Finally, for any major earthquake, there might be few significant structural damage, but it will not collapse. So there will be adequate time for the residents to leave the building. For this reason, we design any structure considering a reduced force than the actual earthquake load. Half of the maximum elastic acceleration is considered, and further it is reduced considering the inherent ductility and overstrength of the structure using a response reduction factor R. This factor depends on the lateral load resisting system, and under table 9, value of R based on different framing system is mentioned, which varies from 3 to 5. For any special moment resisting frame or structure with RC wall, this factor is 5, which means we are considering only 1/10 of the actual seismic force for design. Is it safe? There is a chance that actual seismic force might cross this limit. Then there will be some structural damage, and for that, we need to provide adequate ductility. Not only this, there are several other factors which contribute towards structural strength and stability, like overstrength and redundancy. All this inherent property helps to handle that extra amount of seismic force. For example, factored gravity and lateral loads are used for design, right? Normally 1.2 to 1.5 times of actual load is considered for member design. Along with that, partial safety factor is used for materials which reduce the actual section capacity. Check this bending or compression capacity equation of IS1800-2007, which clearly suggests that we are using a lower section capacity due to material uncertainty. With these factors, actual load is increased and capacity is reduced, which generates a reserve strength in the structure. Apart from this, we always use a section or reinforcement which is more than the required. Consider higher material strength under cyclic loading. Ignore the effects of non-structural elements. All this, including the confining reinforcement provided for ductile detailing, increase the overall strength of the structure. There is another major contributor, redundancy. When yielding starts at a portion of the structure, it does not collapse. Rather, load distribution of redundant structure provides additional safety, which is not considered during design. Finally, to reduce the damage due to additional load, we use ductile detailing. What is ductility and how it affects the structural response? That is beyond today's discussion. We use few additional steps to make the joint and member more ductile by providing additional reinforcement at beam column joint of a concrete frame or extra detailing for steel member and connection. For ductile structure, energy dissipation is more. Also, it becomes soft, which increase the natural period, like a bamboo. That's why ductile structure with higher time period experience a lower seismic force, as we can notice from the response spectrum curve. More ductile structure can withstand higher lateral force without collapse. All these inherent properties hugely contribute towards structural safety and strength. Hence, we can safely reduce the MCE level earthquake to DBE level earthquake using a factor 2R. This reduction can be represented using a curve which suggests how the maximum force is reduced due to ductility, redundancy, and overstrength to compute a more logical force for design without compromising with the safety. To summarize, we can calculate the design horizontal acceleration coefficient AH as per clause 6.4.2. For that, peak response in terms of acceleration coefficient or AC by G is calculated using fundamental natural period, soil condition and damping value. Then it is multiplied with the zone factor to consider peak ground acceleration of different area and an importance factor. This is the MCE level earthquake. Finally, this value is reduced using 2R, considering lower probability of return period and residual strength of the structure. For proper seismic analysis, this basic knowledge is very important, and most of the seismic definition parameters of STAAD for IS1893 is used to calculate the AC by G value. How we can specify these parameters depending on different site and structural condition, that I'll cover in the next part. Stay tuned and keep watching.